Okay, so today's last lecture basically deals with what we call the first and the second law of thermodynamics. So it actually goes exactly like we used to have three laws for mechanics. We remember the law of inertia, the law of acceleration, the one that says F equals ma, and the law of action reaction. So just like we had three laws in mechanics, we have several laws in thermodynamics. And our goal for right now is to cover the first and the second law of thermodynamics. And the first law of thermodynamics is actually a conservation of energy idea. And it goes something like this. Assume that we have a gas which is trapped in a cylinder with a piston, and assume that we give some heat to this gas, and we know the notation for heat is a capital Q. And then the question is, what would the gas do with this heat, with this energy that it receives? Part of this energy is used by the gas to do work. So what do we understand by the gas does work? Basically, if the pressure increases, the gas will act with a force upon the piston. It will push the piston upwards. And while pushing the piston, so what does that mean? Acts with a force. The force displaces its point of application. Therefore, the force does work. So again, part of the energy that the gas receives is used to do work, therefore to push the piston. And another part goes into literally increasing the temperature of the gas. But the temperature of the gas is connected to the internal energy, because we remember from the previous lecture, the internal energy of the gas, depending on the type of gas, monoatomic, diatomic, polyatomic, has these expressions: 3/2 number of moles are temperature, or 5/2 number of moles are temperature, or 7/2 number of moles are temperature. So basically the internal energy depends on the temperature of the gas. So the moment part of the energy that the gas receives is used to increase its temperature, that means the internal energy will change. It will have a certain 3/2 nRT initial, and then after it receives heat, it will have 3/2 nRT final. Therefore, a change in temperature means a change in internal energy. So this here, the fact that the energy, that the heat received by the gas is used by the gas to do work and change its internal energy, this is actually the first law of thermodynamics. We're looking at the first law of thermodynamics, so this idea Q equals work plus change in internal energy as the gas goes through those very specific transformations: isobaric, isovolumetric, isothermal, and then we add two more: adiabatic and cyclic transformation. So let me keep this mathematical formulation of the first law, and let's take transformation by transformation and analyze them. So let's say that first the gas goes through an isobaric transformation. So what was the isobaric transformation? The pressure stays the same, right? So we heat the gas and we allow the piston to move freely. What does that mean that the pressure stays the same? Because the pressure is always equilibrated by the atmospheric pressure and the weight of the piston. So if I allow the piston to move freely, that means at any moment the pressure inside equals the pressure from outside. So an isobaric transformation means the gas will have a certain pressure initial, volume initial, temperature initial, and a certain amount of substance, and goes into same pressure, right, isobaric, a different volume, a different temperature, same amount of substance. So let's look at this first law. My goal here is how do I calculate the work done by the gas in an isobaric transformation? So let's remind ourselves, work is force times displacement. Which force? The force that the gas acts upon the piston. It pushes the piston up, therefore this is the displacement, V. How am I going to calculate the force that the gas acts upon the piston? Well, I know that the pressure, which I wrote it as P initial, but actually is the same pressure, right? It does not change. So the pressure equals force exerted on my piston divided by the area of the piston itself. So that was the definition of pressure, force that acts upon an area divided by the area. And that's the reason why pressure is measured in newtons per meter squared. Therefore, this force that the gas acts upon the piston is going to be the pressure of the gas times the area of the piston times this displacement. But then the area of the piston times this displacement is actually a volume, right? The area is meter squared and the distance is meter. So if you multiply, it's meter cubed. So it's a volume. Which volume? So the area of the piston times the distance, it's basically volume final minus volume initial. That is area times displacement. So it's V final minus V initial, which is actually delta V, right? Changing volume. And in an isobaric transformation, this is as far as we go at this moment in physics 2111. We acknowledge that the amount of heat that we give to the gas, part of it is going to be used by the gas to do work, and that work is going to be calculated using the formula, the constant pressure times the change in volume, and the other part of the heat will be used to change the internal energy of the gas, therefore change its temperature. So in the case of an isobaric transformation, that's the only thing that is new. We wouldn't know how to calculate the work done by the gas. Pressure, which is the same, times the change in volume. So that would be the idea of isobaric transformation. Good. Let's look at isovolumetric transformation. Isovolumetric transformation, we remember, it means that the volume of the gas stays the same. So basically, you can give heat, but you've put a stop to the piston, so it cannot move up, it cannot move down, so the volume stays the same. That's an isovolumetric transformation. When I'm looking at Q equals work plus changing internal energy in an isovolumetric transformation, because the volume of the gas cannot change, that means the gas cannot do work, because work is always associated with a change in volume, right? The gas acts upon the piston, pushes it up, and does work, but that automatically means that there has to be a change in volume. Since there is no change in volume, the work would equal 0. What's left from the first law of thermodynamics? Q equals change in internal energy. So how do I look at this? If I keep the volume of the gas which is trapped in a cylinder with a piston, if I keep it constant and I give heat, the entire amount of heat is going to be used by the gas to increase its temperature. So basically heats up. So Q equals change in internal energy with no work whatsoever. Then I have the isothermal transformation. Isothermal transformation means that somehow the temperature of the gas stays the same. So I give heat to the gas, but the temperature is the same. What does that mean, the temperature is the same? When we recall, internal energy is always 3 halves or 5 halves or 7 halves nRT. And the change in internal energy always goes like 3 halves, 5 halves, 7 halves, nR delta T, so change in temperature. Therefore, if the transformation is isothermal, so the temperature does not change, the internal energy cannot change. So the change in internal energy will be 0. The internal energy stays the same value as it used to be. If change in internal energy is 0, then out of this mathematical formulation, Q equals work plus change in internal energy. If this term is 0, it follows Q equals work. So what does that mean? That means you heat the gas and the whole amount of energy that you give to the gas will use it to do work. Which, by the way, in the case of engines, which are always gases which are trapped in cylinders with piston, and you expect the gas to expand and then come back and expand and come back, right? That's how the cars have their engines. Cylinders with piston that goes up, down, up, down, up, down. So in the case of an engine, this isothermal transformation where you give heat to the gas in the cylinder with a piston and the whole amount of energy is transformed into work, this is the best type of transformation because people want the gas to do work. They do not want the gas to simply warm up. So that's the isothermal transformation. Another transformation that we never discussed until now, it's called an adiabatic transformation. What does adiabatic transformation mean? That means a transformation which takes place so quickly that the gas in the cylinder with a piston does not have time to exchange heat with the surroundings. So that type of transformation, very, very rapid, definitely less than 1 second. So that type of transformation in which the heat exchanged with the surroundings is 0, that's called an adiabatic transformation. From this first law, it follows that 0 equals work plus change in internal energy. And basically it says the following. So let's say that the gas does 500 joules of work. In order to have 0 here, that means the change in internal energy has to be minus 500 joules. So that 500 minus 500 gives a 0. So again, the gas did 500 joules of work, and its internal energy basically decreases. Therefore, the gas cools off. And this is how we interpret it. In an adiabatic transformation, the work done by the gas is done on the expense of its internal energy. So the gas doesn't get any outside energy whatsoever because Q is 0. And if it does work, it does it on the expense of its internal energy, and then the temperature of the gas goes down. So that was the adiabatic transformation. And the last transformation, so let me put here case E, is going to be called a cyclic transformation. So what does cyclic transformation mean? That means, for instance, you start with the gas trapped in a cylinder with a piston, and it has a certain pressure, certain temperature, certain volume, and of course, n number of moles. And I don't care through what transformation it goes, but then it has to return back to its original values. That is a cycle. The gas goes through who knows what type of transformations, but for sure at the very end, it comes back to its original parameters. And this whole, usually it's not one transformation, usually there is a chain of transformations so that eventually the gas goes back to its original parameters. But this whole adventure of the gas is called a cyclic transformation. So out of Q equals work plus change in internal energy, one term again is zero. Who will be zero? Change in internal energy. Why? Because if the beginning temperature of the gas is T initial and then goes through I don't know what transformations, but it ends also at the same T initial temperature, that means the internal energy, which depends only on temperature, does not change. So if the internal energy does not change, then change in internal energy is zero. So in a cyclic transformation, change in internal energy is zero, and it follows Q equals work. More or less, the cyclic transformation has kind of the same outcome as an isothermal transformation. In both of them, since the temperature of the gas initial and final is the same, change in internal energy is zero and Q equals work. So whatever energy you give to the gas, it will be transformed into work. So that's a cyclic transformation. Now, this Q equals work plus change in internal energy. Here, there is a very important sum to pay attention to. Who does work? Does the gas do work, or people do work upon the gas? What does that mean? If the gas does work, that means the gas pushes the piston up and the volume increases. If that's the case, the work, since the volume final is more than volume initial, the work is positive. So one sign convention is work done by the gas is positive. If you do work upon the gas, and how do you understand that? You press the piston down, so you're the person doing work. Volume final is less than volume initial, therefore the change in volume is negative. So work becomes negative. So bottom line, one sign convention is work done by the gas is positive, work done upon the gas is negative. So let me write down this. So sign conventions. So work done by the gas is positive, and work done upon the gas is negative. So that's the sign convention that applies to work. Then we have a sign convention that applies to heat. And actually, we already pointed out that sign convention for heat when we were talking about How much heat do you need to give a substance of mass m in order to change its temperature by a certain amount delta T? And we said, well, the formula is Q equals mc delta T. And there, at that moment, I used to say, every time the object receives heat, its temperature increases. Therefore, in mc delta T, T final is more than T initial, Q is positive. So heat absorbed by the system is positive, and every time the system releases heat in the atmosphere, its temperature decreases. So if you're thinking about mc delta T, temperature final is less than temperature initial and delta T becomes negative. So Q released by the system is negative. And that sign convention applies also to this Q, which enters the first law of thermodynamics. So Q absorbed by the system is positive, and Q released by the system is negative. So these are the sign conventions for Q, for heat, and for work. There is no sign convention for change in internal energy. Why? Because change in internal energy is very clear. It's 3/2 or 5/2 or 7/2 and R delta T. So however temperature final is with respect to temperature initial, the change in internal energy could be positive or negative. Let's go over example 1, which is worked in this PDF. It says this: the pressure of an ideal gas is cut in half slowly while being kept in a container with rigid walls. So they're talking about a gas, they're talking about keeping the gas in a container, and it has basically a constant volume. So it has rigid walls, so nothing changes volume-wise. So what are we talking about? An isovolumetric transformation. And it says this: in the process, 465 kilojoules of heat left the gas. And there are two questions. How much work was done during this process, and what was the change in internal energy of the gas during this process? So this problem, this example, deals, of course, with the first law of thermodynamics. First things, you have to identify the type of transformation. And the moment they say the gas is in a container with rigid walls, that means an isovolumetric transformation. You've decided it's an isovolumetric transformation, then you go back to the formulation of the first law, which says Q equals work plus change in internal energy, and then you recall, if it's isovolumetric, so the volume does not change, there is no work. The gas doesn't do work, you didn't do work on the gas. So work is 0. If work is 0, it follows from the first law, Q equals change in internal energy. And now you reread the problem, and it says, in this isovolumetric process, 465 kilojoules of heat leave the gas. And now you're saying, Q is 465 kilojoules, right? Which is 465,000 joules. But if you pay attention to the formulation, this amount of heat left the gas. And then you go to the sign convention and look at this. Q released by the system is negative. So Q released by the system is negative. So actually the sign for Q has to be negative. or 65 kilojoules. So their question is, how much work was done during the process? Answer, work is 0. And what was the change in internal energy of the gas? You know that change in internal energy equals Q. Since Q is negative 465 kilojoules, then change in internal energy is equal Q, so it equals negative 465 kilojoules. How am I interpreting this? This means that internal energy final minus internal energy initial is a negative number. So internal energy final is less than internal energy initial. That means temperature final is less than temperature initial. So basically the gas cooled off. That's the understanding of change in internal energy negative certain amount. That means the temperature of the gas decreased. But this is a problem which is amazingly simple in a way. You identify the type of transformation, you go back to this one, you decide if any of these terms is 0, and then you just pay attention to the sign convention. And the sign conventions apply either to heat or to work. Okay? Good. So that's in a nutshell the first law of thermodynamics. So again, it is basically a conservation of energy. You give energy to the gas, part of that energy the gas uses to do work, and the other part to change its internal energy, therefore change its temperature. Second law of thermodynamics. So let me clean up. Okay, so the second law of thermodynamics refers to engines, and to be very precise, we call them heat engines, and it's exactly the basic of the engine that works in a car. So it's true. In a car, you don't have one cylinder with a piston, you have several, right? That's why there are cars with 6 cylinders and more, and so on and so forth. So there are more cylinders with pistons. But bottom line, it's the same idea. There is some, we call it working substance, which is usually air with gasoline drizzled inside. So that's the working substance, but bottom line, a glorified gas that goes through all kinds of transformations. And in some transformations, the gas will expand, will do work. In some other transformations, the gas will come back to its original volume. Therefore, these are all cyclic transformations. So gas starts in a certain state, goes through several transformations, come back to the same state. So a cycle, a cyclic transformation. And in that, so this is the working substance. And this working substance, of course, in order for that gas to expand and then come back and so on and so forth, there will be some transformations in which it receives heat, and the heat which it receives, since it's always from very high temperatures, is going to be called Q off, and the notation is Q subscript H. So there are some transformations in which the working substance receives some energy, and that's going to be called Q hot. There are some transformations in which the working substance does work, and there are some transformations in which the working substance releases heat, which is, of course, the gases which are expelled by all the cars in the atmosphere. So that is heat released in the atmosphere, and since the atmosphere is considered to be like a huge thermostat with cold temperature, that heat is going to be called Q cold or Q subscript C. So basically, a working substance receives heat, does work, expels some heat. It always goes through a cyclic transformation. So always cyclic transformation. And since it is a cyclic transformation, so initial and final parameters are the same, we remember that means no change in internal energy, because internal energy depends on temperature. If initial and final temperatures are the same, that means there was no change in internal energy. So change in internal energy is zero. If change in internal energy is zero, from the first law of thermodynamics, which says Q equals work plus change in internal energy, that term becomes zero, so Q equals work. So how am I looking at this? What Q, what work? Work is the work done by this substance. What Q am I considering here? You have to consider the overall heat exchange by the working substance with outside. And the overall heat exchange means sometimes it receives, sometimes it expels. So under this Q, it's actually Q hot plus Q cold. And that equals work, right? So the first law of thermodynamics, since changing internal energy is zero, means Q equals work. But you have to take into consideration all kinds of heat, not only Q hot or only Q cold, everything. And everything means Q hot plus Q cold, and then it will equal work. The most important thing for a heat engine is its efficiency. Efficiency of a heat engine is defined as work done by the working substance, because that's the plus for a human being when the piston goes up. That's the work done by the working substance, divided by how much energy you've input. And you've input Q hot, because that's the energy which is input into this system. So the efficiency is defined as work divided by Q hot. Now, if instead of the work, I'm going to use Q hot plus Q cold, and everything divided by Q hot, and then I divide each term of the numerator by the denominator, and I'll have Q hot over Q hot, which is 1, plus Q cold over Q hot. And if we're looking at this formula, efficiency of a heat engine equals 1 plus Q cold over Q hot, people might think, oh my gosh, so are you really saying that the efficiency is more than 1 because it's 1 plus something? And by the way, efficiency 1 is the same as saying efficiency 100%. And the reality is, no, the efficiency is never greater than 1. Why? Because of the sign convention. Because Q hot is heat absorbed by the system, so Q hot is always positive, as opposed to Q cold, which is expelled by the system, therefore Q cold is negative. So, for instance, I would give my working substance 700 joules of heat, 200 joules of work it does, and 500 joules it expels. But sign-wise, this is plus 700 and this is minus, what did I say? Minus 500, because plus 700 minus 500 gives me 200, which is the work. So bottom line, Q hot is positive, Q cold is negative, and in my example it was 1 plus negative 500 divided by positive 700, so it's 1 minus 5 over 7, and it is what it is, but definitely less than 1. So that's the observation here, that the efficiency is always less than 1. And of course, the goal of people is always to get cars with efficiencies better and better and better, so better and better engines actually. So there is a lot of effort put into getting these efficiencies as close to 1 as possible. By the way, we're really far from that. Usually cars have efficiencies of 0.2, which means 20%. Usually that's the efficiency of a car. So since engineers are trying hard to do the efficiency closer and closer to 1, people were thinking, what is actually the meaning of efficiency 1? And you can imagine if you're looking at efficiency equals work divided by Q hot. If you want this to be 1, that means work equals Q hot. So what's the understanding? If work equals Q hot, that means the working substance receives some heat and it transforms entirely into work. There is nothing expelled. That would be an ideal case, and it is literally impossible to achieve. So that is actually the second law of thermodynamics, and it sounds a little bit, I don't know, very childish in a way to say that it is impossible to have a heat engine which transforms entirely the heat that it receives into work, because that's actually the formulation of the second law of thermodynamics. But the reality is that it has such deep implications, this idea that you can never have a cyclic transformation in which Q hot is entirely transformed into work and basically Q cold is 0. So it has such important outcomes that this statement has been made into the second law of thermodynamics. So what's to remember from here? This thing over here, right? So in problems, usually people are asked to calculate efficiency of a certain engine when work is known, Q hot is known, and you have to calculate. Or sometimes they are asking, by the way, how much is Q cold? How do we get that? We know that Q hot plus Q cold equals work. So if this is given, this is given, you can get that one. So these and these are important expressions here. And there is one more thing before I finish this. There is an ideal cyclic transformation. And this ideal cyclic transformation, it cannot be done in reality, but it was imagined by a French engineer whose name was Carnot. Now I can't remember his first name, whatever, Carnot. Therefore, that's known as the Carnot engine. But it is literally an imaginary situation. It cannot be made in reality. But the importance of that Carnot engine is that it establishes how much is the maximum efficiency that a real engine can obtain. So the efficiency of a Carnot engine, and the notation is going to be E and subscript is C, which stands for, so this is efficiency of a Carnot engine. This equals 1 minus T cold over T hot. So how do we interpret this? If I know that the working substance receives heat, is Q hot, from some thermostat which has a very high temperature, and you know that very high temperature, and you also know that the working substance expels heat into the atmosphere, and you know the temperature at which it expels, and that's going to be T cold. So if you know T hot and T cold, and mind you, T hot and T cold are both capital T, therefore they are both in Kelvin. So if you know that and that, and you calculate 1 minus T cold over T hot, you get the efficiency of a Carnot engine. Therefore, any real engine which works between the same extreme temperatures, a certain T hot and a certain T cold, so any real engine has to have efficiency less than the efficiency of the Carnot engine. So efficiency for any real engine has to be less than the efficiency of a Carnot engine. So this also and this idea are also important. There are, in my opinion, so at the end of this PDF file, there are problems 4, 5, and 6, which are literally trivial problems only to apply these things, right? So, for instance, let's work together one of them. So, would you have a preference for 5 or 6? Or no preference whatsoever? No? Okay, let's do problem 4. It says this: a heat engine. Now, it doesn't say anything about Carnot, whatever. So a heat engine takes in 360 joules of energy from a hot reservoir. So receives 360 joules of energy from a hot reservoir, performs 25 joules of work in each cycle. And the question is, find the efficiency. And we go to this and we say, well, so I'm going to work this example high up here. So this is the example which is actually number 4 from the homework. If it says that the working substance takes in 360 joules of energy from a hot reservoir, that's Q hot, and since it is absorbed, it's positive, so positive 360 joules. Then the working substance performs 25 joules of work. And we remember the sign convention for work. Work done by the system is positive. So this is plus 25 joules. And the first question is, let's calculate the efficiency. And we go back to this and we say, well, efficiency is by definition work divided by Q hot. So it's 25 joules divided by 360 joules, and apparently this is 0.069, which otherwise multiplied by 100 is 6.9%. So efficiencies are okay if they are declared either like a decimal number or multiplied by 100 and we say whatever percent, right? So that was the first question. Then the second question, so part B, is saying, what is the energy expelled to the cold reservoir? So they ask how much is Q cold? And then we go back to this expression, for instance. I know that Q hot plus Q cold equals work. So Q hot is 360 joules. Q cold, I don't know, but work was 25 joules. Therefore, Q cold is 25 joules minus 360 joules. And this is going to be negative 335 joules, right? So negative 335 joules. And we notice how nice that Q cold comes with a negative sign, because that's exactly how it should be. Since it is expelled and released by the gas, it has to be negative. So that's, for example, problem number 4. Problem number 5 and number 6 kind of go the same way. Very easy, but definitely nice problems for tomorrow's test, actually. Okay, so I'm done. And last test tomorrow. So Daniela, are you taking the test from 1 to 3 or later in the day? What?
I'm not taking 1 to 3.
Ah, you're taking it later, right? Okay. All right. Okay. Okay, good. So if there are no questions, then good luck for tomorrow. And, kind of thank goodness that everything is over, right? Okay, bye.
Thank you.